I'd like to continue on here in section 6.6 with frames. Now 6b20, this problem here is a frame. We have a force being pushing it here. It's basically shoving the whole thing this way. This is a two-force member, which means that it's reacting back like that. So let's draw the reaction forces that we know of or that we can identify. I'll try an AY and AX, FY, and Fx. Again, I don't know for sure if those are the right directions. I'm just going to assume them for right now. But I do know that this EX is going in this direction because as this is pushing it this way, it's going to have something pushing it back. Now, how many unknowns do we have? 2, 4, 5. When you have 5 unknowns in reactions, it's pretty difficult to make very much progress before you break it apart. So I'm going to jump immediately to breaking it apart. So I'm going to draw this free body diagram of that part. Of this part, I'll draw this free body diagram. Recognizing this is a two-force member, so looking carefully at how two-force members work, it looks like it should be in compression as you're witnessing the problem. So draw it as a compression member. So that means CX and CY are both pushing in, BY and BX are both pushing in. That would make it a compression member. Obviously, CX and BX are equal, BY and CY are equal. These forces transfer equal opposite to here. These forces transfer equal opposite to there. So draw the forces correctly, of course, and then where do you get started? I don't know anything about this. I don't know anything about this as far as any forces are applied. I can't solve for anything. However, I do have this 200 here, so I can start here, some of the moments about A, and I can make some progress. I can find CX. Once I find CX, I can find BX. Once I find BX, I can find BX over here. Once I find BX over here, I can solve for EX. It's kind of that simple as you just kind of walk through the whole process. But you can look through my solution here of what I've done. And I started here. I found those there. I found EX just like that. To find the rest of the forces, the rest of the reactions, just kind of walk through the process again. Here's some of the forces in the X and Y on this member. Use some two-force rules here to find out something about that. And then do forces in X and Y over here on this member. So this is just a problem-solving tip and hint. When you're doing these things, make sure the free body diagram and the equations that apply to the free body diagram are close together. They're lined up. You can do it horizontally and put the equations like that, free body diagrams vertically. Or you can do these things like I did on this one, where the free body diagrams are horizontal, but then the equations are vertical. However way you want to arrange your paper, I don't care, but please do not have a free body diagram like here and then have the equations someplace else on the paper. That makes it pretty confusing to grade. It doesn't make logical sense for you. You'll get mixed up too, especially if you have to go back and troubleshoot your work or look and see what you did. So just keep things in a logical, organized way, please. I got a couple other things I just want to show you here in the examples. I believe there's two ways you can describe frames. Obviously, there are more than two ways you can describe them, but I'm going to call them simple or complex based on whether or not you can discover the external reactions without breaking it apart. For example, this is a simple problem with a two-force member, and you can find the external reactions using the solution 1 technique if you assume that it's a two-force member. However, solution 2 is available here too, and what it does is if you break it apart and don't assume a two-force member, then it becomes a little more complex, and that's why I call it complex if you have to break it apart to find the external reactions. Simple if you can discover something about the external reactions without breaking it apart. Here's another example. This is a problem, another example problem in the book. There's a lot of unknowns here, and so this is definitely, I would my description calls it a complex frame because you have to break it apart to find the reactions. Then here's another example. In this case, you can discover the external reactions here without breaking it apart. So I call that a simple frame. So for your work, don't focus too much on whether it's simple or complex. However, when I do exam problems, I'll probably take that into account, whether I consider it a simple frame or a complex frame. So here's what I would consider a simple frame because, well, you'll see here in a second, but this problem, we have the only forces that's going on here is this couple, and what we're looking for is the reactions at A and D. And so let's set this up. Let's draw a free body diagram. So I'll just kind of duplicate what we've got here. And I got another component, and that is like that. There's going to be a force at D, dx, then force here at A, y, and ax, and of course the couple of 600. All right, let's see what we can find. Let's sum of the forces, or sum of the moments, and see what we get. Sum of the moments about A is equal to 0. So I got minus, whoops, that should be 60, not 600. There, minus 60 plus dx times 0.5 equals 0. So here's my lever arm for dx right here. Got that couple going that way. So I can solve for dx right there. So I'm going to say dx is equal to 120 pounds. All right, what else can I find? Sum of the forces in the x is equal to 0. And I can see that ax is equal to 120 pounds. Sum of the forces in the y is equal to 0. And you can see that ay is equal to 0. Okay, so I've solved for all of the reactions. What we're looking for, however, is what is the what's happening here at B, and also that little force there I'll call Cy, right in there. It's a normal force that's between those two. So the only way to discover those guys is to break it apart and do the separate analyses. So I'll just do this. Okay, so I know D. I don't know this Cy. By an unknown, and Bx is unknown. However, I can sum of the forces in the x. And so here I can discover that dx minus dx plus bx is equal to 0. So bx is equal to 120. What else can we find? How about sum of the moments about some point? I'll do sum of the moments about b is equal to 0. So in this case, I got minus Cy times this lever arm, which is here, which is 4, plus dx times 0.5 is equal to 0. So here I got Cy is equal to 15 pounds. Oh, and now I'm getting someplace. And then sum of the forces in the y is equal to 0, and I can find that by is equal to 15 pounds. Okay, so now we've got all of the components defined. Everything is worked out. One thing you can do is check to see what it, if you got it correct. So let's do that. Let's draw the free body diagram of the bottom link, and let's just see what I got. Got an AY, an AX, got a couple, 60, CY, BY, and BX. Okay, again, these transfer equal opposite from here. If I draw them this way up there, I have to draw them opposite like that. So let's just solve for one equation, or just to check my work. I'm going to sum the moments about A equals 0. So here I've got minus 60, which is the couple, minus Cy times 3, plus By times 7 equals 0. And I can see that minus 60 minus 15 times 3 plus 15 times 7 equals 0. And indeed, that does equal 0, and I check, and so I've basically proved that I set it up and did it correctly. So I encourage you to do that if you want. Well, the last one I want to go through with you in this video is this complex frame, 676. It actually has 4 members. 1, 2, 3, 4. It's also important to recognize 2 force members, and you can see that this one is a 2 force member and this one's a 2 force member. This one is not, because it has that force being in the middle. So let's go ahead and write or draw the forces on the picture here. So this is the resultant force of this distributed force times this distance, and that is 400 newtons per meter times 4.5 meters, so that's 1,800 newtons, and it acts at a distance of 2.25 from that line. The reaction forces are AX and AY and BY and BX. Okay. All right, I can find out something without breaking it apart. If I sum the moments about A, I have BY times this lever arm and 1,800 times this lever arm, and I can find out BY. Once I have BY, I can sum the forces in the Y, and I can find AY. All right, so I've made some good progress there. How about this 2 force member? This 2 force member is in the horizontal configuration. And if we recall from our study in trusses, that if there is no angle associated with this, then there can't be any Y forces associated. So this is a good simplification. You should know that the dx and cx are going to be the only forces on there. There will be no Y forces. This one is also a 2 force member, and looking carefully at the geometry here, this is just going to kind of draw a little triangle here. This is 2. This distance here is 3, but this distance is 1.5, so this is inside distance is 1.5. And actually this is a 2 or a 3, 4, 5 triangle, which means that this component here of EF will be the 4/5 component, and this component of EF will be the 3/5 component. So let's draw a free body diagram of this thing, and that's what I've done over here. Again, assuming that this one is a 2 force member in compression, the force is going in, that means it has to go that way on this side. If I assume this one is in compression, don't know for sure, then it's going in like this, and so I have EF, 4/5 EF, and 3/5 EF. Then I've got the reactions that I've solved for. All right, let's see if I can find something. I have BY right here. And BY, if I sum if I look at this free body diagram, if I sum the forces in the Y direction, I have BY and 3/5 of EF. And so I can solve for EF just like that. And indeed, it shows up that it is in compression. It is 3,375 in compression, or positive in the way I drew my arrow. What else can I find then? If I could sum the moments about C, I should be able to then solve for BX, which indeed I did. So I've solved for BY up here. I have BX here. Now what do I do with BX? I look at this plus this, and these are all the forces I have in the X direction. So if I go back over here in this direction, then some of the forces in the X for the entire structure, I can find AX is equal to 0, which is a little surprising. You know, you wouldn't think that you'd have a 0x force with this big 1,800 Newton distributed force pushing on that, but that looks like it is the correct answer. So, all right, well, I hope that is helpful for you.